Hello and welcome to my YouTube channel. In this video we're gonna take a look on how to spawn objects in a surface delimited by a spline inside Unreal Engine 5. Let's dive in immediately and let me explain the purpose of this video. Imagine you have a custom surface like this created using the spline tool inside Unreal Engine 5, and you want to spawn meshes, foliage, anything inside this surface. For example, this point, and in this video we're gonna take a look on how to determine whether this point is inside this custom surface or not. To do so, we're gonna use an algorithm called the raycasting algorithm. The raycasting algorithm is a geometry technique used to determine whether a point lies inside, outside, or on the boundary of a polygon. The algorithm works by casting an imaginary ray from the point in question and counting the number of intersections with the edges of the polygon. The fundamental idea is based on the even-odd rule, which states that if the number of intersections is odd, the point is inside the polygon. If even, the point is outside. For example, here we have 1, 2, and 3 intersections with the edges of the polygon, so the point lies inside. If we take another example, for example, another point here, and let's cast a ray. Let's now count the intersections. We have 1, 2, 3, and 4. The number is even, so the point lies outside the polygon. So now, after explaining the raycasting algorithm in the most simple way, let's take a look to this page I found on the internet that has explained the algorithm more precisely in more details. I will put the link in the description for you to check it out. And we have here in the bottom a C++ algorithm, an algorithm written in C++ language that explains how to do it in the most simple way. So I took almost what is written here, I translated it into Unreal Engine C++ API vocabulary so we can have the same name of the structure, the same name of the classes that we're gonna use inside our blueprint, so that we don't have any confusion after that. So let's take a look at the translation of the code I've done. We have our function in question. This is the function that we're gonna use to determine whether the point is inside or outside the polygon. The function takes the point that we're gonna test and the polygon, our custom spline created inside Unreal Engine. So the point will be a vector of point, and the polygon will be an array, a list of points, and these points will determine the vertices of this polygon. So it's just gonna be a list of points in the space. So our function will return a boolean. It's a flag to say yes, it's inside, or no, it's outside. We're gonna go through all the vertices of the polygon. This is why we have our for loop. And then we have just 2 conditions to determine whether the point is inside or the outside. So let's break through these conditions and let me explain to you how we're gonna do this. Our function is mainly based on 2 conditions. Let's take a look at both of them in more details now. Before that, let me explain the J index here. So the I index is just an index, goes from 0 to the last point, and the J index is created to design the previous point to this I index. For example, let's go back here. If we name our point here A, B, C, D, E, and F, So if we start at the point A, the point 0, we're gonna have the point F here as the previous point. So the J index will be for the point F, and the I index will be the point A, and the segment that we're gonna test the intersection with is the segment formed by the IF. So it will be this segment. And we're gonna test the intersection between the point in question that we're gonna test and the ray casted from this point to the right with this segment FA. Just put this in mind, the J is the previous point, the I is the point we are testing. Let's get back. So we have two main conditions. Let's start by the first one. So this one. This condition consists on checking the y-coordinate intersections. This means that the condition checks if the y-coordinate of the point that we are testing lies between the y-coordinates of the edge endpoints, the point in question, not the point in question, the two points forming the segment, the FA that we just talked about. And we're gonna test whether the y of the point that we are testing lies between the two y's. Get back to our graph and let me explain to you. So here we have the 2 points, we have the segment, and here we have the two y's. So here we have the y for the F point, and here we have the y for the A point. And now in this case, we are just gonna test whether the y of this point lies here, to say that we have an intersection. For example, if we take a point that is here, and we want to test the intersection of our point with the segment AF. We are just talking about the segment AF, we're not talking about the other polygon. Let's cast our ray, and we see that there is no intersection with the point with the segment AF. We're not talking about all the polygon. Here we are in the for loop, and the for loop we're gonna test each segment. We are testing each segment of the polygon, and that means that we're gonna come here to the segment EF, we're gonna get to the segment ED, DC, and BC. But what I'm explaining here, I'm explaining, for example, for the segment AF, we don't have an intersection, so there's no need to get back to get to the second condition, because we have a y that is not in the range of the two endpoints of the segment, so we can move on to the next segment. And if we take a look at the point that we are testing here, this point lies between the two y's of the endpoints, so we possibly have an intersection with the segment. But this point, because it's out of the range, we will not have an intersection with the segment in question. So this is what this condition, the first condition, consists of. Let's move on to the second condition. The second condition. So this condition consists on calculating the x-coordinate of the intersection point and compare it to the x-coordinate of the point we are testing. This formula consists on computing the slope of the edge, and this formula will give us the value of the x-coordinate for the intersection point, and then we're gonna compare the point x to the intersection x. If the point is less than the intersection point, that means we have an intersection between the ray casted from the point to the right with the segment we are testing. If it's equal, this means that it's on the edge. If it's greater than, so the point lies on the right side of the edge we are testing, so we don't have intersection. Let's get back to our scheme. Here, let's take this point, for example. This point lies in the range of the y, so we will calculate this x coordinate. Here we have our x coordinate, and we see that it's greater than the x coordinate of the point we are testing, so we have intersection. But if we take a look at this point, for example, this point lies between this point's y coordinate lies between the a and f, so it verified the first condition. But if we take a look at the intersection here, if we have this intersection with a segment, and this will be our x value, we see that the x value of the intersection, or x coordinate of the intersection point, is less than the x coordinate of the point you are testing. So we don't have intersection between the ray casted to the right from the point we are testing to the segment AF we are testing. At the same time, we have intersection here because the x of the intersection is greater than the x of the point we are testing. So that explains the algorithm, and that explains the two main conditions that we have in our algorithm that we're gonna use in the blueprints. So if we verify the two conditions, that means we have an intersection with the edge. So we will set our Boolean to the logical not, to the not value of the same variable. So this we can do this in two ways. For example, we can have an int intersection count. It will be 0, for example, here. And if we verify the condition, the intersection count will be incremented by 1. And here at the end, instead of returning the Boolean that we are switching, we can return this. And this means that the intersection count is odd. If it's even, we don't, the point lies outside, and if it's odd, the point lies inside. So these two methods are the same. Now that we understood how our algorithm works, let's dive into Unreal Engine 5 and let's start creating our class, our actor, that will spawn our meshes inside the surface. Here we have Unreal Engine 5 with a basic empty level. Let's start by creating a folder named maps in which we will save our map. Let's create a second folder named blueprints. Right click in the content browser, select blueprint class, select actor and name it BP spawner. Double click on the BP spawner, and here we have our blueprint. Here we'll have the the components, and here we have the variables. Here we'll have our functions. So let's start by adding a new component, a spline component. So this component will be the spline that will delimit our surface. So let's select the second spline point, hit delete to remove it, right click on the first spline point and hit spline generation panel. This will allow us to create a template, just some generic shapes using the spline. Let's hit rectangle. Let's take the branch right and let's make it 10 meter by 7 meter. Let's close the spline generation panel. Let's here select the fourth input point. We don't want to have 2 points on the same location. Let's hit delete and let's get here and just take the closed loop so we have a closed surface. After this done, hit compile and then save. Let's go back to our level, open the content browser, drag and drop the BP spawner, and here we have our surface, our actor spawned with the template, with the default surface as a rectangle. We can go here, right click, add a spline point, drag it to create some custom shapes. So add a spline point here, let's do the same here again, and let it be a little bit complicated like this. So here we have our surface, and let's start implementing our algorithm inside the blueprint so we can validate or we can verify whether the point we are selecting are inside or outside the surface. Now let's go back to our blueprint and let's create our first variable. Will be the number of number of meshes to be placed, number of instances will be an integer. Let's give it a default value of 100. And then let's start by creating our first function, the function that we have created here, the is point in polygon. Let's copy it. Let's go under function, hit the plus button, create a new function. Let's name it is point in polygon. So as we have here the point, the function output will be a boolean, the function return will be a boolean, and the function parameters will be an f vector, the point, and an array of f vector will be the polygon. Let's do the same thing. So under input, let's hit the plus button, and here let's call it in point. Let's select vector here. Let's add a second parameter. Let's call it in polygon. And let's make it an array. Here we have two parameters, one as vector and the second as an array of vectors. Let's go to the output here. Let's hit the plus button and let's call it b is inside. Let's make it a boolean and let's make it a single. And here we have our function that have as parameters the point, the the polygon, and as return we have a boolean. So let's put it aside and let's start creating our function. So let's create a comment to have better understanding on the function in question. Okay, so this is our function that we have just created, and let's create it under C++ and let's make it in the blueprints. So we will start by making a local variable called num points. So the num points here will take the number of vectors inside the polygon array. So let's take it here and get the length. Now let's put it here and promote to local variable. Let's call it num points. Here we'll set our local variables. Then we'll have another local variable will be the b return will be our return value, will be a boolean, and let's set it to false in the beginning as we have here. Let's forget about the intersection count and let's remove this. We will have this method instead. Now we have the for loop. So let's search for loop, select the for loop, and our for loop will go from 0 to the num points, like this, and here we have the stop index and inclusive, so we need to do a -1 unless we will be out of range. So this is our loop. To better organize our codes, let's create our index I, let it be an integer, and let's create our index j. So our index I will be our index, and our index j will be the index I plus the num points -1 modulo the num points. So it will be the index I plus the num points -1, and the result will be modulo the num points. This will be our index j. Okay. So we just finished the first line here, and let's move on to the two conditions. Let's get our first condition, and let us be more clear in our code. So I think this is good here. Okay, so let's add a new comment. And let's put our condition to have a close look to our condition. So in our condition we'll have the polygon I, the y coordinate of the polygon I. Let's compare it to the y coordinates of our point in question. and let's verify that the point is in the range of the two endpoints. So let's get the n polygon here, and let's get the n point, our two parameters. Okay, so the first we'll test it, we will get the I index here. Let's break our vector to 3. Let's split it to 3 variables, the x, y, and z. And let's start by doing the first comparison. Is the polygon I greater than the point y? Okay, so this is our first condition. Let's make a not equal, and let's get the same thing, put it down here, and instead of index I, let's get the index j, and verify that the index j, the y coordinate of the index j is greater than the y coordinate of the point we are testing, and put it here. So here we have our first condition. Here we have our first condition. Let's make a branch, and let's move to the second condition. So let's create a comment, and let's get our second condition right here. So in the second condition, we will need the endpoint, we will need the n polygon, we will get the polygon I, and we will get the polygon j. Okay, so the first comparison is, so let's split these two structures here. So we have the polygon j, the x coordinate of polygon j minus the x coordinate of the polygon I. So the x coordinate of the polygon j minus the x of the polygon y. So we have the first part, we will multiply it by the point y. Let's go down here, let's split it, the point y minus the polygon I dot y. So polygon y, the point y minus the polygon y, polygon I dot y. So this one. Then divided by the y coordinate of the j minus the y coordinate of the I. So here we have it divided by let's get the j. So divided by the polygon j, like this. So the y coordinate of the j minus the y coordinate of the I. here we have it multiplied, and then we will add to it the x, the polygon, the x coordinate of the polygon I. So polygon I, here we have it. Okay, so here we calculated the intersection point. Now let's compare it to so let's compare it now to this. And here we have our second condition. Let's put it together. Okay, we have the two conditions, and now we have the end node. And let's put it in the branch. So here we have the condition. Let's put it here. Let's remove this. And now we're gonna set the B is inside to the not B is inside. So if it's true, we're gonna get this. We're gonna set it to the not Boolean. Okay, and at the end of the for loop we will return our B return. So this is it. This is our function. Now let's move on and create another function that will use this one to spawn, to verify different points. Now that we have created the function that checks whether the point is inside the polygon or not, let's move on now and create a second function that will allow us to generate different points and check whether they are inside the polygon or not, and then this function will allow us to spawn the meshes we wanted to spawn. So let's click on the plus sign under functions and create a new function called spawn meshes, for example. So this will be the function that will use the other one to generate the foliage. So let's take the function that we have created before. We need two parameters as input. We need the point. The point will be generated randomly inside the polygon and the polygon in question. So we need to start by filling the polygon. Let's create a new local variable, call it spline points. It will be an array of f vectors. And then we need to fill this array of vectors. Let's start by getting the spline component. Let's get the number of spline points. We're gonna loop over the number of spline points. Let's subtract 1 because the for loop has its top index included in the loop. So to avoid having an out of range error, let's do -1, and then here let's get location at spline point. The spline point will be the index, and the coordinate space should be the world location, the world coordinate space. So here we have the point. We need to do an add, and we will add the point we wanted to add. And here we should be good at filling these points array. After doing that, we will start the main core of the generation of the points and verifying whether they are inside or outside the surface. So to do so, we need to have our while loop. This while loop will run until we get the number of instances done. So let's create a new local variable called valid instances, and it should be an integer, and this integer should be 0. Let's put it at 0. And then we will take the valid instance, we will compare it to the number of instances, and where if the number of the valid instances is less than the number of wanted instances, we stay in the loop, else we get out of the loop. So this is our main condition. And now we need to generate a random point inside the surface. So we will take all the surface. Here we gonna get this spline component. We will get bounds. Get component bounds will give us a box that covers all the bounds of the spline. So we will have two types of bounds. We will have a sphere bounding and we have box bound. We will use the box. So let's get random point in box. The center will be the origin of the bounding box, and the half size will be the box extent. Let's promote this to local variable and call it candidate point. We will set it, and now we will have our function that will take as input the candidate point, and the second input, the polygon, will be this points we have filled in the start of the function. And here we will have a branch. If the point is valid, we will draw debug point. This will be just for debug, to have a visual appearance to the points we have selected. The point should be the candidate point here. We will give them a size of 5, a color will be black, and a duration of 10 seconds. And then we will have our validate instances counter should be incremented by 1, and this should do it. To avoid having debug points one on top of the other, let's, in the start of the function, do flush persistent debug lines. This will erase all the persistent lines, and this allows us to draw new points here to avoid having points on top of the old points. So this should do the work. Let's take a look. Let's make this function callable via the editor. Let's tick this box, compile, save. Go back to our level, select our object. We will have the number of instances here as a variable we can edit. Let's keep it at 100, and we will have a new button that will call the function that we have created, these spawn meshes. If we click, we will have points spawned inside the surface we wanted. Let's create 500 points. Let's spawn it, and here we have different random points generated each time. Let's put 1,000 points, and there it is. So to give you an idea about the points in general, let's take this, let's duplicate it, and if the point is not valid, let's spawn them under red color, and let's take a look. Let's have 500 points. Let's spawn. They should be under red color. Let's compile, let's go back, and let's spawn. Here you see we have the red points that are the points that are not valid, and they are the points generated randomly in the bounding box. At the same time, we have the black points are the valid points that are spawned inside the surface, the wanted surface. Now if we remove the case where we don't want the point to be spawned, we will have only the points, the valid points, that will give us the opportunity to spawn different meshes inside this custom mesh. Let's add a new spline point here, and let's put it like this, and spawn meshes. We see that points are generated there also. Now that our algorithm is working properly, let's move on to the last part of the video where we spawn meshes instead of the debug points. So we don't need this function anymore. We need the candidate point. Remove this function. Let's put the incrementation aside. We don't need the flush persistent point anymore. So let's compile, let's save. Let's put this to avoid having an infinite loop if I click by mistake on the function. So now we need to have our mesh. Let's add a new variable. Let's call it static mesh. This will be the mesh we want to spawn. Let's search for the type as static mesh, object reference, compile, and go. Let's go to add here. Let's add a new hierarchical instance static mesh component just to have better stats. And let's go to our constructor, and let's get the hierarchical instance static mesh component. Let's do set static mesh. Let's get a reference to our static mesh and set it there. Okay. So here, each time we edit the static mesh, we will set the new static mesh to the hierarchical instance static mesh component. Let's save. Let's go back to our mesh, to our spawn mesh. In case the position is valid, we will have our hierarchical instance static mesh component. Let's call the method add instance. It's in local space. We want it in world space, add okay, we should, okay, so they changed the API. We have this tick box here, we can set the world space. So we will have, we'll add instance, let's break the transform, let's split it. The location will be the candidate point, and let's have a random rotator. Let's split it, and let's just put the random on Z. Yeah, we can just put the random on Z, and here let's get random float in range to just set the scale. Let's put it between 0.5 and 1.5. Let's put it here, and let's tick the world space. Let's save it. Let's get back to our level. Here we have a new variable called static mesh, in which we can put a static mesh we want. Let's go to the content browser here. Let's click on the add icon. Let's add the feature or content back. Go to content, add the starter content back. Here we'll have some shapes, some bushes that we can use. Click on the SM Bosch, get back to the spawner, use this asset, and let's click on spawn mesh, and here we have our bushes. You have our bushes in different varieties, different scales, and different yaw rotation. But here we have forgot to do an important thing, is each time we call this function, we should remove the old instances so that we don't have instances getting along with the old ones. So let's call the function clear instances at the beginning of the function. Let's save, let's get back, and now let's spawn meshes. This will remove the old instances and now create new ones. Let's take a close look. We have some small bushes, we have some big ones, and they are in different locations each time. We can spawn 50, for example, we'll have a few. We can spawn 1,000 and we will have a lot. Also, we can add a new spline point here, for example. Let's get it there. Let's spawn meshes, and we will have our meshes spawned in different locations because we have changed the shape of the surface. Also, we can edit the mesh, and here we'll have the new mesh. You can wait for the shaders to compile, and here we have new meshes spawned instead. So that's it. So thank you guys for watching. That's it for this video, and see you next time.